Hey, today I would like to share some of our findings on this topic, solutions to the Diophantine equation x squared plus 16 times 7 to the power of b equals to y to the power of 2r. Let me first give you some introduction related to Diophantine equations. So this is an equation in which only integer solutions are allowed. So when studying Diophantine equation, we are interested on whether a solution exists. So if a solution exists, then how many of them? And is that possible for us to represent the solutions using a general formula? And I believe that the formula's theorem is one of the most popular equations since 1637. And the proof was successfully published by Andrew Wiles in 1995. So a considerable amount of literature related to the Diophantine equation has been published over the years. And here's another popular equation, x squared plus c equals y to the power of n, where x squared is at least 1 and n is at least 3. And this problem was investigated since 1850. And there are many problems that could be derived based on equation 1. For example, c could be a constant here. And there are many results related to this type of equation, especially when c is in between 1 to 100. Similarly, c could be replaced by a fixed prime. And lastly, c could also be replaced by two fixed primes here. And this is our focus in this talk. And this talk, we are going to determine general formula that provide integral solutions to our equation, which is x squared plus 16 times 7b equals to y to r. Here's a definition. So for any Diophantine equation, the pair of integers x, y, r is a generator of solutions to the equations. And this result was published in 2013. It says that the generators of solutions to the equation x squared plus 2a times 7b equals to y to r are given by either this set of solutions or this set of solutions where p is in between 0 to a exclusive and q is in between 0 to b inclusive. Here's our main theorem. So we show that the generators of solutions to the equation, which is this one, have the following forms. We classify this one into three different cases. When I equals to 3t minus 2, we have these two equations. When I equals 3t minus 1, again, we have these set of solutions. And lastly, when I equals 3t, we have equation 6 and equation 7. And here I represent the ith set of non-negative integral solutions associated with each b. So here's how we prove theorem 3. We first substitute a equals to 4 into the generators in theorem 2. And we will obtain equation 8 and equation 9 here, where this is the range of p and this is the range of q. Now, if we fix the value of b and consider all the possible values of p and q here, then we are going to obtain many different set of solutions here. For example, when b equals to 1, we obtain three different sets of non-negative integral solutions, and they are arranged in a descending order. Similarly, when b equals to 2, there are 5 different sets of solutions. When b equals to 3, we have 6 different sets of solutions. And now we are going to represent these numbers in this form. The reason is we are going to create a relationship between the numbers in these three tables. All right. Now, by grouping all these numbers based on the value of I, for example, when I equals to 1, these are the equations that we are going to obtain. And because b is any positive integer, this will go up to infinity. And therefore, to obtain a general formula for this one, we apply induction on b, and hence we obtain xb1 equals to this. And this is the general form to represent this scenario. Secondly, if we apply induction on b again, then we obtain yrb1 equals to this one. By using a similar approach, we can also obtain the general form for all other values of I, which is I equals to 2, 3, 4, and so on. And now this is what we are going to obtain. And by observations, these set of solutions can be classified into three categories based on the value of I. For example, when I equals to 1, 4, 7, and 10, this one will go into the first category because they have a similar form. And this will be in the second category. And this is in the third category. And now we have three different cases here. This is when I equals 3t minus 2, 3t minus 1, and 3t, where t is any positive integer. And in order to obtain a general formula for xbi and yrbi, again, I'm going to apply the induction on the value of I. For example, when I equals 3t minus 2 by induction on I will obtain these two equations. So if I now exclude the first term in these two equations, we can see that the remaining terms will actually form a geometric series. That means we can actually now simplify these two equations by using the method of geometric progression. Now, if I suppose the common ratio V equals 1/7, and this is the initial value, and this is the number of terms, the two equations can now be simplified into this form. And this is exactly what I want to prove in this theorem. And by using the similar method, and we can now complete the proof for two other cases. That is when I equals 3t minus 1 and when I equals 3t. And this completes the proof for theorem 3. And this lemma, we will determine the range of I associated with B, where B is odd and when B is even. So based on the previous result, we know that we have to consider these three cases. If we first consider I equals 3t minus 2, we know that we have to consider equation 2, which is this one, xbi equals to this. And because xbi is non-negative, that means the terms in the parentheses here must greater than 0. And therefore, we obtain the following inequality. By solving the inequality, we obtain I less than 2/3b plus 2.06a6. This implies that I is less than the ceiling function of this equation. And therefore, when B is odd, we obtain this. And when B is even, we obtain this range for I. So by doing the same for the two other cases, then we basically complete the proof in this lemma. And next, we have theorem 5. In this theorem, we show that when B is even and when I is 3/2b plus 2, we have this and this as the generators of solutions to our equation. You can imagine this is just a special case to our main theorem. And in fact, we have two special cases here. And the next one I will show you in theorem 6. So because B is even, so I let B equals 2h and I substitute B equals 2h into here. And then I obtain I equals 3h plus 2. And obviously, the set of equations 3h plus 2 is a subset of the set of equations 3t minus 1. And this tells us that we have to consider equation 4 in theorem 3, which is xbi equals to this. Now, if I substitute I equals 3/2b plus 2 into this equation and simplify the equation, I am going to obtain xbi equals to 0. Next, if I want to show that yrbi equals this one, then I have to consider equation 5 in theorem 3 now. By doing the same, if I substitute I equals 3/2b plus 2 into this equation, then simplify the equation, eventually you can see that yrbi equals to this one. And this is exactly what we want to show in this theorem. And next, this is another special case. The difference here is just the value of I is reduced by 1. I is now 3/2b plus 1 instead of 3/2b plus 2. We show that if this condition is satisfied, then xbi equals to this and yrbi equals to this are the generators of solution to our equation. And for the interest of time, I'm not going to show the proof in this theorem because the proof is very much similar to what we have in theorem 5. And I think these are the only results that I would like to share with you today. Thank you for your attention.